Good afternoon, everyone. My name is Zheng. The title of the presentation is Input to State Stability in Different Norms for One-Dimensional Parabolic PDEs. This is joint work with Professor Guchuan Zhu from Polytechnic Montreal. In section 1, I will introduce briefly the ISS of ODE systems and the ISS of PDE systems. In section 2, I'd like to introduce a gap in the IS analysis when we use the Lyapunov method. At the same time, I'd like also to propose a possible solution. In section 3, I will present the main problem considered in this work and the main results. In section 4, I will provide some concluding remarks. Let's look at the ODE system. Here X is the state variable. U represents external inputs. The notion of input to state stability was introduced by Zheng in 1980s. This notion can be used for characterizing the effect of U on the stability of the system. More precisely, we say that system 1 is ISS if there exists functions beta belonging to KL class and a function gamma belonging to K class, such that this estimate holds true. It should be mentioned that for ODE systems, the existence of an ISS Lyapunov function implies the IS of the system. Conversely, if the system is ISS, then there must exist an ISS Lyapunov function. The study of ISS of PDEs starts around 2010. In general, external disturbance can appear in the domain or on the boundary of the domain, or in domain and on the boundary of the domain at the same time. Comparing with the ODE case, ISS of PDEs is much more complicated. I'd like to provide two conferences here. Like ODE systems, for PDE systems, the existence of an ISS Lyapunov functional also implies the ISS of the system. Therefore, constructing an ISS Lyapunov functional is a key step in the ISS analysis when the Lyapunov functional is applied. However, even if a PD system is ISS, we don't know in advance whether an ISS Lyapunov functional exists or not. This represents a big problem in the IS analysis of PD systems. The fact for parabolic PDEs with in-domain disturbances is that VW, defined like this, can be chosen as a suitable ISS Lyapunov functional for establishing the ISS in LP norm when P is larger than 2. I'd like to ask, is this form of VW applicable for establishing the IS in LP norm for PDEs when P is less than 2? Let's look at this example. Here D represents the in-domain disturbance. If P equals to 1, note that the derivative of ds is singular at 0. So how to calculate the derivative of L1 norm of W? Now, if P is larger than 1 but less than 2, by integrated bypass, we have these equalities. However, for this integral, how to calculate this term? In fact, this term is also singular at 0 when P is less than 2. So we meet a problem, that is to say, singularities may arise in establishing the IS in LP norm for PDEs when P is less than 2. To overcome this problem, we introduced a novel approach. More precisely, instead of constructing an IS as Lyapunov functional directly, we construct its approximations. The main technique is based on the application of a C2 continuous convex function, rho tau s. We construct a rho tau s like this. Indeed, this function has the following good properties. These properties will be used for the ISS analysis. Now let's look at the idea of constructing approximations of Lyapunov fractionals. The idea is based on the application of rho tau s. Indeed, for any L1 norm, for any L1 measurable function W by 3a and 3c, we have this estimate. Note that the integral of rho tau W can be bounded by the L1 norm of W and tau. So if we let tau tend to 0, then we have this limit. Therefore, we can take the integral of rho tau W as an approximation of this functional. Similarly, for LP measurable function W, the integral of the piece out of rho tau W is an approximation of this functional. It should be noticed that the choice of rho tau s is not unique. In fact, we can construct rho tau s like this. Here, A0 can be an arbitrary positive constant. Let's look at the main problem considered in this work. We consider the following parabolic PDEs in divergence form. Here, LTW is a linear part of the equation, and HW is a nonlinear fraction. D represents the in-domain disturbance. Assume that A, B, C, D, H are all smooth functions and satisfy certain conditions. Let W0 be an initial data. We say this system is LRISS in the spatial LP norm with respect to the in-domain disturbance D belonging to this space. If there exist functions beta belonging to KL class and gamma belonging to K class, such that this estimate holds true, we see that the system is LRISS in W1P0 norm if this estimate holds true. Let's look at the main results. The first one is concerned with LRISS in a spatial LP norm. Indeed, under this condition, we can prove that system 4 is LRIS in LP norm for any R. And if A, B, C are independent of the time variable t and satisfy this condition, then we can also prove the system is LRIS in LP norm for any P and any R satisfying this condition. The second result is concerned with the LRIS in a spatial W1P0 norm. And these conditions, we can prove that system 4 is LRIS in W1P0 norm with respect to T belonging to this space. Here, P and R can be arbitrary constants satisfying these conditions. The main idea of the proof is simple. Indeed, we can choose this integral as an approximation of this functional for establishing the LRIS in LP norm when P is less than 2. And we can choose this integral as an approximation of this functional for the LRIS in W1P0 norm. Then, by fundamental computations on the derivative of these two integrals and using basic properties of the tau s, we can prove theorem 1 and theorem 2 respectively. At last, I'd like to provide some remarks. Indeed, any C2 continuous functions root S satisfying these properties can be used for establishing the LRIS estimates. It should be mentioned that the proposed method is also suitable for establishing the LRIS in LP norm and W1P0 norm for any P and any R satisfying these conditions. In our future work, we may apply the proposed approach to establish LRIS estimates in different norms for parabolic PDEs, which are defined over higher dimensional domains and with different types of boundary conditions. That's all. Thank you.